Hello, ladies and gentlemen. My name is Jerzy Baranowski, and welcome to our final part of multiparameter models in STAN lecture. In this lecture, we present the most complicated model we have so far, a model that presents the so-called Bioassay experiment, which considers the aspect of experiments on animals, in particular giving rats the doses of certain medication and checking how this dose is lethal, at what level dose it is lethal. In this example, we will use binomial distribution, but we will supplement it additionally with parameter transformations in order to keep the variables constrained between 0 and 1, and at the same time using linear model for the Bioassay with respect to our initial regressor. The model is relatively simple, but it includes some elements that we want to do, and also we will use this model to estimate so-called LD50 statistic, which is commonly used in the pharmaceutical industry, which is what this is called little dose 50, which means at which dose 50% of cases ends lethally. So please listen to the rest of the lecture. Thank you very much. We'll be considering something called Bioassay experiments. Generally, the experiment is conducted on animals, for example, mice or rats, and such experiments are conducted in a way that you have a set of animals and you provide these animals with various doses of certain compounds. So, for example, you have 5 mice and you inject them with certain doses of medicine, all of them the same dose. Then you conduct an experiment with the same series of mice, but with different dose. So, and the results from that experiments are usually binary. So you have the either alive or dead, tumor or no tumor, something like that. And the data from such experiments consist of tuples of three elements, which will be either first of all will be the dose levels, usually measured on the logarithmic scale, in order to make certain different scales easier, those are given to n animals, and y of them resulted with a positive outcome. And this example comes from Gelman, where this was investigated more analytically. We'll be doing it in STAN to see how it works. And what we are doing here, like from packages, nothing much special. From Cypher, we will be taking function xpit, which is used for inverse logistic computation, which we'll be using for some plotting. And we have our own special function here, which is called ribbon plot. And a few words about ribbon plots before we move to the data. This is the plot that we can use to visualize our predictions or our models for situations when our model has a varying variable. For example, a linearly varying variable, in this case a dose, which will be represented from -1 to 1, logarithm of -1 to 1, so it covers the in logarithm of 10, it will cover dosages from 0.1 up to 10. And the ribbon plot is generally when you have, for this predictive value, you have computed certain, you obtained certain results, you have certain predictions, you can compute quantiles for each of those samples. So you get what is the median for each of value of this dependent or this independent variable, and then you can construct the quantile curves that are representing each of those levels. And ribbon plot visualizes that you start with median, then you have extra 10 plus 10 minus 10, also 60% and 40% quantile. Then you have 70% and 30% quantile. Then 20 and 10, and then you can go for that. So the ribbon plot is kind of like a it's more detailed than the box plot, and not as full as histogram, but it allows us to handle the variation of data in the more dimensional case when we have these varying variables. So we'll be using ribbon plot a lot, especially further when we move to regression analysis. So the ribbon plot looks like this, and it's encoded in this form. If you want to use it, feel free. So let's go to our data from our experiment. This is the data set obtained from literature, where we have a dose of we have four different doses, each was provided to the NI animals. In this case, in all trials, there were 5 animals. For the smallest dose, none of the animals died. For the largest dose, all of animals died. So we had this situation, and we can look at these data, so the number of deaths to the number of animals as a proportion of them, and we can plot them with respect to given dosage. Just again, you can see the doses here. Units, here we have actually units because we have a logarithm of gram per milliliter of medicine. And in here we have unitless value of proportion of deaths. So you have either none deaths or all deaths, or 30% or 60% or 20%. So generally, we can see certain things. First of all, there is some kind of sigmoid-like relationship. This is not a linear relationship. Something is going on here, and we have to look on that first. Second of all, this is bounded values because we cannot have more than 100% of deaths and no less than 0 deaths. So this is important. We can consider the outcomes of each of 5 animals in a group as exchangeable because we have no reason to think that mice in one group were differing from each other. Of course, we cannot replace mice between groups because they are given different doses. So it can be reasonable to assume that in one experiment the probability of death for each of mice was constant. Depending on the dosage, of course, but the dose was fixed. So in one experiment, in one batch of mice, the probability was constant and equal for each of those. So generally, for each of those samples, we have the binomial distribution. The binomial distribution, which will be here as that number of deaths is conditional on the theta parameter, and it's given by binomial distribution with n, in this case 5 trials with the probability of theta. And we need to have some kind of relationship between dose and probability. And this is how most of modeling happens in statistics, that you have parameters and then you assign certain functions of those parameters in order to obtain the relationship between predictors and the outcomes. And this is the so-called structural modeling, that you provide certain structure. And we start with, well, very simple assumptions. There is some kind of linear relationship between the dose and the probability of death. But of course, such linear relation would be unbounded, and we have 0, 1. So here we will use transformation. We assume that our theta has to be located in the interval 0 from 1 because it's probability. So we can use the logit function in order to get probability from 0, 1 scale to the plus minus infinity scale, or using inverse logit function, which we'll be using here, to transform our unbounded values from alpha and beta times xi into the bounded 0, 1 interval. And because of that, we can now get the likelihood of our for our model. And our model, our likelihood is, as you can see, binomial probability that logit, inverse logit function of alpha plus beta xc is our theta, which is here up to the power yi, and here is the power of 1 minus the same value to the power of ni minus yi. And this is the likelihood for single experiment. So generally, our posterior for the entire set of experiments, assuming that those experiments are exchangeable with each other, we can now get we have the prior for alpha and beta, so our coefficients, which are obviously independent from number of animals and are independent from the dosage, because we assume that they are constant, independent of the dosage. So because we have relationship in theta depends on the dosage, but the coefficients of these relationships are not depending on xi. And of course, because of this exchangeability, we can assume that this our model will be prior for parameters alpha and beta multiplied by our binomial likelihoods for each of the experiments. Now we need to assign the prior. And well, here we'll get to the suggestions of such priors, because here we have logit transformation, so we are very close to something called logistic regression. And for that, in case of scaled parameters, and our predictors are between -1 and 1, so they are well scaled, it is proposed that to use student t distribution with numbers of degrees of freedom between 3 and 7, and 0 mean and certain scale of that is relevant to the problem. This is, of course, weakly informative prior, because we don't have much more ideas how to model such things. If we had some pharmacological knowledge, we could probably get certain relationships better modeled. For example, if we were sure that the dosage increases lethality, we could assign the positive prior for coefficient beta. So let's get our model for prior predictive checks. So we have our model that will need the number of measurements, so how many trials we'll perform, then number of counts of animals per experiment. In our data we have 5 per each experiment, but it could vary in different situations. Our model is general, and we provide it with doses of substance per experiment we'll be using from our real data, actual doses. For parameters alpha and beta, we will be sampling them from the student t distribution with 5 degrees of freedom, because 5 is a number well in the 3 to 7 interval, and we will be and we assume the scale is 10, so we'll have very well spread of parameters. And for each of those alpha and beta, we conduct the separate simulation for each of the doses. So we compute the theta from the theta parameter from the binomial as inverse logit of alpha plus beta times the dosage, and we'll perform it for each of the dedicated number of experiments. So compilation of this model we'll do off screen. We are using the cache model, and we set up parameters of our models. Again, because we are not fitting, we are just sampling, so using fixed parameters solver. And our simulational data consists of the same number of experiments with the same number of rats per each of experiments, and with doses provided by our dataset. So we sample from our model, and we get our parameters. We get our points alpha, beta, and yc. Let's start with our non-informative student t prior, and generally we get a large spread of our parameters, because we haven't assigned any correlation for those variables. We don't have any systematic relationships. Here, each of those we assume is independently distributed. As you can see, there is a large spread because student t distribution allows for heavier tails in order to move. And if we consider our we will be predicting our values. So for each of the experiments, we get the appropriate number of potential deaths per doses. And here, as you can see, well, our values are still probable because they happen in the intervals. But as you can see, there's some systematic characters of those prior predictive models. We won't care about it too much because it's generally justified. Our model allows us to get higher values of alpha and beta. If we have higher values of alpha and beta, our inverse logistic function will move to saturation because it is kind of linear in the middle, sigmoidal in the middle, but then it starts saturating for large negative and large positive values. So if we would get a consistent sign from alpha and beta times xe and will be either big or either small, then we will be thrown either to strongly negative or strongly positive values. So our model will indicate large probability or very small probability of death, depending on where it lands. So these are all those things that are more tailed here, not located near the center. And because there's enough of them, then the histograms look like they look. But again, we don't care about it too much because it's still our predictions are kinda in realm of possibility. They are not contradicting the data. They are just suggesting that it's not that probable if we have no conditioning of the data. What can we do? We can see how our relationship would look like. And this relationship, of course, is because of a giant randomness, as you can see. This relationship is either very skewed towards negative or positive values. Depending on where we are going, it will get easily saturated or easily on positive or negative values. And our ribbon plot gives us full coverage. Everything is possible in such sampling. The median is very irregular, which is generally normal in such case because we have very random samples. So, of course, our samples are generally possible, but not that much, and we have this spread here. So, our model, our prior predictive model, does not contradict the possible data. We can say that it passed our prior predictive checks, at least at the moment. If we will start to work on it later, maybe we have some better ideas. So let's move to the posterior inference, and let's create our actual model. Our actual model consists of data block is very similar, but we've added additionally the outcomes of each experiment in order to we have again two parameters, alpha and beta, which will be transformed for each of those experiments. And here we use the transform parameters block. Transform parameters block will be used to compute theta parameters. Theta parameters will be actually not be sampled from the distribution, will be conditional on alpha and beta, but it makes our representation a bit easier in what we want to do. So each of those theta parameters will be, each element of vector of theta parameters will be generated by inverse logic transformation of alpha plus beta times appropriate dose of minus. So again, as two videos before, we are using the logarithmic formulation of our model. So instead of sampling from each of those distributions, we will be adding to the target variable, which is a system variable from Stan, get in the model block. We are adding either logarithmic student distributions for alpha and for beta, and we are adding the binomials for each of those yk, dependent, of course, on number of animals in the experiment and the theta parameters that were computed in a transformed parameters block. So that's a use for transform parameters to make the code easier, to get some manipulation that might be convenient for the computation. And for our generated quantities, we'll simulate the outcomes from our model. So when we are generating samples, we will be also sampling from using the same theta we'll be using to sample possible values. Here in the model we are fitting the data, and when is fit, then we can get our value of theta and get it to and compute right generated quantities. So again, compilation is done offline. The data is the same as previously, but with added numbers of depths. We do some sampling. No problems. However, as you can see, we have the adapt delta parameter added here. It was happening because of certain divergences that were happening in the model. Increasing adapt delta helped, but this is something that we'll cover at a later date. And so using all the diagnostics, everything went very fine, and we have our model. We extract fit parameters, and let's start looking at what's going on. Let's first start with our posterior samples. As you can see, the posterior distribution for alpha and beta is much more condensated than the original one. Original one gave us samples everywhere. Here we have them very thickly packed here in comparison with prior samples. So the posterior samples for alpha and beta, which generally we could devise certain units for them, but it's really pointless because our results after transformation is still the probability, which is dimensionless without any doubts. So our posterior samples are much more bounded, but they are not contradicting the prior. The prior allowed them here. It was consistent with what we are sampling here, which is just more focused because we have conditioned it on data. If we look at the marginal distributions, we can see that alpha parameter is relatively small, around between 0 and 4, and beta parameter is rather strong. So the relationship between those is, first of all, it's certainly positive. So it increasing the dose increases the lethality according to our model, and we have a large spread of we have much less confidence in beta than in alpha. So this is the much more. And for comparison, we can use from AVIS, we can use joint visualization of our posterior. This time we can see the marginal distributions with the KDEs and also the plot with KDE. KDE, that is kernel density estimator, is a method for estimating probability distributions with a smooth curves. So let's look how our posterior generates predictions. As you've seen before, our standard model generated predictions of outputs, and let's see how these predictions of experiment results, you can see here, are corresponding to the actual data we had. And the correspondence is very nice. For each of those doses, the percentages of deaths or number of deaths are very consistent with original results. So for the maxima of the histograms are located either at or very close to the actual observed values. So we can see that our model is well representing our data. There is no conflict here with the data, despite the fact that the values are integers. And of course, we can again try to visualize the relationship between the dose and the lethality. And we can draw again few simple draws from the posterior distribution. So you can see most of them are some kind of sigmoids. This one is, as you can see, a bit broad, but when we condensate all of that into the ribbon plot, then we have actually we can observe very nicely. First of all our measurements are close to the median, which is good indicator, and also all of them fit well inside the ribbon. So our ribbon represents how we have the uncertainty of our predictions for each of the doses, and this is the possibility of such visualization. So ribbon plot allows us to see how well inside of our predictive distribution our actual data fits. That's one thing, and gives us certain information about the uncertainty of our predictions. We are not only interested in the uncertainty of parameters, because those parameters we have here. From that, we would be able to get theta for each of those doses and see their variance, but that their variance would be much lower than the one observed in the rainbow plot of the prediction, because prediction adds additional randomness to that. This is our model which we can use to generate data, and these data are consistent with our observers. And finally, we go to the question that is typically asked in such situations, so-called LD50 parameter. This is the dose level at which the probability of death is 50-50. Because our model is a logistic model, we are looking for value where alpha plus beta xi is equal to 0.5. And however, we need to remember that this parameter makes sense only if increasing doses increases the lethality, because that's only a situation where that makes sense. So beta has to be 0, and we'll greater than 0, and for that we'll just take those beta greater than 0 and use it for sampling our values. So what is important here? We are not taking mean, we are not taking median of our measurements. We just take samples, and from those samples we estimate the parameter of interest, which is much more robust than considering the values. Because, for example, if we had some negative values of beta, the mean would be strongly skewed away from sensible results. The other thing is that maybe we should consider modeling beta with positive enforcing prior, which is matter that you might consider in your own investigation of this model. So we get those samples, and we can get the estimate of LD50 conditional on beta greater than 0. Of course, in our case, all the betas were greater than 0, so the problem was irrelevant. Looking at that, we get some kind of spread of our information. We get a histogram of LD50, which is the division of minus alpha divided by beta, and the median of this distribution is minus 0.11, with a confidence interval between minus 0.25 to 0.08. And our initial intuition, if someone asks it, that's, oh, this interval contains 0, so we don't have the information about the relationship. Is it positive or negative? No, the relationship is always positive. The relationship is always positive. But the issue is here that remember that this dose is at the logarithmic scale. So if you move from logarithmic scale to real scale, to actual scale, then the doses in question would be varying from minus 0.025, so that is the 10 up to minus 0.25 to 10 up to 0.08. So this is our confidence interval in the scope of actual data of actual medicine dosage. So it will be between 0.56 gram per liter per milliliter up to 1.2, and with the median given as 10 up to minus 0.11. So we 10, and this will be 0.776 gram per minute. So we've took it, of course, simplified but full dose from the model. We started with data and problem description. So we have our data and our problem description. We formalized our assumptions here based on data analysis, exploratory data analysis, and logical analysis of the experiment about exchangeability, about constraints on the variables. We selected prior for our parameters when we developed the likelihood. We did the checks for the prior. It makes sense? The data aren't completely outside of the interest, and we got that the relationship is possible to generate a relationship that might make sense. So this would be also useful. Then we fitted the data. So we've performed analysis of the conditional distribution. And from that, we got the posterior predictive distribution of outputs, which is consistent with our data. So again, it's nice, and this is a good base to see how our model looks like, and we can verify it with ribbon plot, and we can start to answering the actual research question. So what's the LD50 value is, and we get the 90% confidence interval, we get the value, we can see that histogram is sums up our uncertainty.
Ladies and gentlemen, thank you. This concludes our lecture on multi-parameter models, from which we've started with very simple model of generally mean and variance, or scale and location, and we've considered multiple aspects of such model. Then we moved to the multinomial model, so we had constraint parameters in form of simplex. Then finally we concluded with Bioassay experiment, and we had a nonlinear transformation of variables. As you can see, construction of a multi-parameter models really allows us to do very complicated methods or complicated transformation in order to obtain the final result, which will be a model of phenomena of interest. That's why it was important for you to remember about things like predictive checks, about highlights of model comparison, about robust models, and about using priors and priors to simulate the results to see how our distribution behaves. So hopefully the lecture was interesting for you, all three parts, and next time we will move to more complicated things, which are linear models. Maybe not that complicated, but a bit more advanced. Thank you very much for listening, and have a nice day.